NEC section 230.90 states that service conductors shall be connected to the service disconnect, and any other circuits or equipment shall be connected downstream of the service disconnect. The proposed design taps into service conductors upstream of the main panel, thus violating this requirement. Next, let's consider overcurrent protection for the new feeder. NEC section 240.21 mandates that branch circuits be protected by overcurrent devices rated not greater than the ampacity of the branch circuit conductors. Furthermore, NEC section 240.4b specifies that the sum of the overcurrent protection devices shall not exceed the ampacity of the conductors they protect. Without the required information such as the rating of the service conductors, the method by which they are protected, the rating of that protection, nor the length of the tap, it is impossible to determine if these requirements are met. Now let's discuss the neutral to ground bond. NEC section 250.24b states that the neutral conductor shall be bonded to the grounding electrode system at the service entrance or as close as possible to it. Connecting upstream of the service disconnect and before the neutral to ground bond violates this requirement. The lack of grounding and bonding details is another area of concern. NEC section 250.1 requires all electrical systems to be grounded and bonded. The absence of grounding and bonding details makes it impossible to determine if these requirements are met. To achieve code compliance, the proposed configuration could be modified. Firstly, connect the new panel downstream of the service disconnect following NEC section 230.90a. Secondly, properly size and install overcurrent protection for the new feeder in accordance with NEC sections 240.21b and 240.4b. Thirdly, bond the neutral conductor to the grounding electrode system at the service entrance or as close as possible to it following NEC section 250.24b. Fourthly, provide grounding and bonding details that meet the requirements of NEC section 250.1. Let's delve deeper into each of these points, starting with NEC section 230.90a. This section is a cornerstone of safe electrical installations. It dictates that the service disconnect, which is typically a main breaker, must be the first point of disconnection for the entire electrical service. Connecting anything upstream of this disconnect means that the new panel would not be protected by the main service disconnect. This scenario poses a significant safety hazard, as an overcurrent or fault in the new panel could potentially overload the service conductors without tripping the main breaker, leading to overheating, insulation damage, and potentially a fire. The importance of overcurrent protection, as outlined in NEC sections 240.21b and 240.4b, cannot be overstated. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds the safe ampacity of the conductors. This prevents the conductors from overheating and potentially causing a fire. To properly size these devices, it is crucial to know the ampacity of the conductors being protected. The ampacity is determined by several factors, including the conductor material, size, insulation type, and insulation conditions. Without this information, it is impossible to select the appropriate overcurrent protection devices, and the electrical system would be vulnerable to overloads and short circuits. The neutral to ground bond, as mandated by NEC section 250.24b, plays a critical role in ensuring a low impedance path for fault current to return to the source. This low impedance path is essential for the rapid operation of overcurrent protection devices during a ground fault. When a ground fault occurs, current flows from a live conductor to ground. If the neutral to ground bond is not properly established, the fault current may not be high enough to trip the circuit breaker or blow the fuse, resulting in a persistent ground fault that can pose a shock hazard. Grounding and bonding, as required by NEC section 250.1, are fundamental to electrical safety. Grounding provides a connection to the earth, which helps to stabilize voltage and limit the voltage rise during a fault. Bonding, on the other hand, connects all non-current carrying metal parts of the electrical system together, creating an equipotential plane. This ensures that there are no voltage differences between these metal parts, which can prevent electric shock. The absence of grounding and bonding details makes it impossible to verify that these crucial safety measures are in place. To further elaborate on the TAP rules mentioned earlier, let's discuss the specific requirements that need to be met for TAP to be code compliant. The TAP rules are outlined in NEC section 240.21b. These rules allow for conductors to be tapped from a larger feeder or service conductor without overcurrent protection at the tap point, provided certain conditions are met. Firstly, the tap conductor must have an ampacity of not less than 1/3 of the overcurrent protection device protecting the larger feeder or service conductor. Secondly, the tap conductor must terminate in a single circuit breaker or set of fuses rated not more than the ampacity of the tap conductor. Thirdly, the tap conductor must be protected from physical damage. Finally, the length of the tap conductor is limited depending on the specific application. In some cases, the tap conductor can be no longer than 10 feet, while in other cases, it can be no longer than 25 feet. It is also important to consider the available fault current at the service entrance. The available fault current is the maximum amount of current that can flow during a short circuit or ground fault. This value is determined by the utility company and depends on the size and impedance of the transformer supplying the service. The overcurrent protection devices used in the electrical system must have a sufficient interrupting rating to safely interrupt the available fault current. If the interrupting rating of the overcurrent protection devices is less than the available fault current, the devices may fail to interrupt the fault, which can result in equipment damage and potential injury. Another critical aspect of electrical safety is proper conductor sizing. The size of the conductors used in an electrical system must be adequate to carry the intended load without overheating. The NEC provides tables that specify the ampacity of different conductor sizes based on their material, insulation type, and installation conditions. When selecting conductor sizes, it is essential to consider the ambient temperature and any dirting factors that may apply. Dirting factors are used to reduce the ampacity of conductors when they are installed in conditions that can cause them to overheat, such as in conduit with other conductors or in areas with high ambient temperatures. The grounding electrode system is another crucial component of an electrical system. The grounding electrode system provides a connection to the earth, which helps to stabilize voltage and limit the voltage rise during a fault. The NEC specifies the types of grounding electrodes that are permitted, as well as the methods for installing them. Common grounding electrodes include ground rods, ground plates, and metal underground water pipes. The grounding electrode system must be properly sized and installed to ensure that it can effectively carry fault current to ground. Bonding is equally important in maintaining electrical safety. Bonding connects all non-current carrying metal parts of the electrical system together, creating an equipotential plane. This ensures that there are no voltage differences between these metal parts, which can prevent electric shock. The NEC specifies the methods for bonding different types of metal parts, such as metal conduits, metal enclosures, and metal equipment. Bonding jumpers must be properly sized and installed to ensure that they can effectively carry fault current. In addition to the NEC requirements, it is also important to consider local codes and regulations. Local codes may have additional requirements that are not covered in the NEC. It is essential to consult with the local electrical inspector to ensure that the electrical installation complies with all applicable codes and regulations. Let's consider the implications of connecting to a wire that might be owned and controlled by the utility. Typically, the utility company owns and maintains the service conductors up to the point of connection to the customer's service entrance equipment. Tapping into these conductors without the utility's permission is not only a code violation, but also a potential legal issue. Furthermore, tampering with utility-owned equipment can be extremely dangerous and can result in severe injury or death. It is crucial to ensure that all electrical work is performed by qualified and licensed electricians. Licensed electricians have the training and experience necessary to perform electrical work safely and in accordance with the NEC and local codes. Attempting to perform electrical work without the proper qualifications can be extremely dangerous and can result in serious injury or death. In summary, the proposed configuration of tapping into service conductors upstream of the main panel violates several key provisions of the NEC. To achieve code compliance, the new panel must be connected downstream of the service disconnect. Proper overcurrent protection must be provided for the new feeder. The neutral conductor must be bonded to the grounding electrode system at the service entrance, and grounding and bonding details must be provided that meet the requirements of the NEC. It is also essential to consult with the local electrical inspector to ensure that the electrical installation complies with all applicable codes and regulations.